हो गया ना? एप्लीकेशन बेस्ड जो अगर इधर बाजू में पूरा बैठने वाला तो एक मैच मिलता है पूरी एक दो और टिकट दे देंगे तो क्या बोलो लिखते प्राइस एक भी कम थोड़ा ये बड़ा मतलब या प्राइस या कोई तो देखो 20 रुपए
Anybody Santali?
Yes.
Event? Okay. Rest of you have already signed it. Nobody is to be. Anybody remaining to sign? So we have finished the last chapter, right? So we'll begin with a new chapter today, which is work, power, energy. So when we talk about work, it is the physical work, right? So what do we call work? physical work is in physics. So whenever, yes. So energy is capacity to do work. That is correct. But I am asking what is work?
When you apply force on an object and it moves in the direction of the force.
Correct. So whenever you have an object, okay, and if you are applying force on it, right? So under the application of force, if this object moves in the direction of force, let us say it covers displacement S, then we say work is done by this force on this object. So be very clear, who is doing the work? The force. Where is the work done? On the object. When do we say that the work is done? When the object moves under the application of force. Clear? Okay. So how do we define the work done? So work done is defined as product of force with displacement. Got it? Work is defined as product of force and the displacement in the direction of force. In the direction of force. So this is our definition of work done in physics, right? So in short, we write W is equal to F S. So what is the unit then? Unit is Newton meter. Okay, which is also called as Joule. So, Joule. Right? Now this is one situation where we applied the force and the displacement took place in the direction of force. There could be a situation when force and displacement are in different directions. Right? For example, force work done when force and displacement are in different directions. Then how do we calculate the work? See, for example, there is an inclined plane. Okay? And the object is kept here. Right? A person applies a force here. This is the direction of force. But where will this body move now? It will move upward. Till here, that is it. Okay. So the displacement is at an angle, say theta. Okay. So how do we calculate the work done in this case? So let us say we drop a perpendicular from there, from the end where the displacement ends, right? Let's name this as A, B, and C. Okay, what is the direction of force? Horizontal. So we have to find out the component of displacement in the horizontal direction. Then, because force into displacement in the direction of force we want to know. So what is the component of this displacement? It is AC. Okay. So work done in this case is work done equal to force F into component of displacement. Okay. In the horizontal direction along direction of force. Okay, this product will be work done. That is F into AC. Right? Because F is the magnitude of force. And what is AC? Displacement in the direction of force. So how do we find AC? So what is the relation between AC and S? Huh? Since cos theta is equal to base upon hypotenuse, AC upon AB. So this gives us AC is equal to AB cos theta. What is AB? S cos theta. AC is S cos theta. Right? Right? It's important. So for W is equal to F S cos theta. So this is a more general definition for work. So work done is not only force times displacement, it is force times displacement into the cosine of angle between force and displacement. Are you familiar with cos theta, sin theta? Because in CBSE, I think it is introduced in 10th. So there is one more situation. Instead of taking displacement along force, I can also take a component of force along displacement. Right? So I can do that. So for that, what I can do is, now see, where is my force direction? This direction. So I can now extend this line. Right? So this was my force. And then I can drop a perpendicular over here. Right? So let's say I'm calling this as PQ. So if this was my force, E is representing force and this is vertically opposite angle, so it is theta. So what is the other definition? Other definition of work is force, component of force in the direction of displacement into displacement. So I can calculate work in both ways, right? So now what is the component of force in the direction of displacement? It is QA. Correct? Because this is the direction of force and this is the direction of displacement. So force along displacement is QA. This force. Right? So how do we do it? We have extended this line and we have dropped the perpendicular to get a right angle triangle. So what is the relation between QA and F? Because these are the only two things we want, right? Cos theta is equal to, this time it is QA, that is based upon hypotenuse. QA upon, this is PA, which is air movement. So this means QA is equal to P cos theta. But what is PA? F. Right? PA is F. Right? So QA, you will substitute it over here. So what you will get? Therefore, W is equal to F cos theta into S of. So this is the same thing. F plus cos theta or F cos theta is same thing. So what done is either you take force in the direction of displacement and multiply. When the force and displacement are in different direction, you have to take the component of each other in their respective direction. Got it? So that's it. So first you note it down here and then we'll go ahead. Do you want to note down or should I go ahead? Note down? Okay. Because it is all given beautifully in textbook. So if you have the habit of reading it, but this is a small something. See, anybody has any doubt here? See it now. Can I erase the left and middle part? Yeah, good, good. Good. So, we learned that the order is given as it's basically three of you still writing. So let's discuss the spatial cases. I think done. Can I start? Okay. So when is no work done? So from this formula, when the force is applied but no displacement, right? So no work done is the case when force applied results in zero displacement. Then no work done because F into zero, everything zero. So this is the first case for no work done. What is the second case? Theta 90, right? Since cos 90 is also zero. Therefore, when angle between F and S is 90 degree, then also work done is zero. Right? So what is the example for the first case and the second case? Pushing the wall. You are applying the force but no displacement. Okay? So examples are pushing the wall. Okay, no work done. First case. Can you give me example of this? When the angle between force and displacement is 90 degree.
When a person carries luggage straight and
There is nothing. Person is walking, right? Where is the force? mg, right? Excuse me. So force is the weight. Weight is downward. That is the force. So which force is this? Gravitational force. So who is not doing work? The gravitational force is not doing work. Right? What is the force acting? Gravitational force. So no work done. By gravitational force. In this case, right? So because gravitational force, if I draw the diagram, where it is in this direction. So don't get confused by W. It is not work, it is mg. F equal to mg, right? Yes, otherwise you will get confused with this. So this is mg. And where is the displacement in this? What is the angle? 90. The angle between F and S, whenever it is 90, cos 90 is 0. And which force? Gravitational force. No work done by gravitational force in this situation. When a person carrying load. Any other example of 90 degree? What about this? Revolution of electron in orbit around nucleus. Where is the force acting on the electron? What kind of motion is this? UCM, uniform circular motion, right? So, where is the force? Electrostatic force towards the center. Where is the displacement at every instant? Along the tangent. So, the centripetal force and the displacement are always at 90 degree. So any body which is undergoing UCM, no work is done on the body by centripetal force. But it has to be UCM, non-accelerated. Okay. So under any UCM, uniform circular motion, no work is done on the object. Is everybody with me on this? So this is our case 1, no work done. Then case 2. Positive work done. So when is work done positive? When theta is equal to 0, that means cos 0 is equal to 1. Which means when force and displacement are in the same direction, right? So therefore W is equal to Fs cos 0. This is equal to Fs. This is positive. So example. So when force F and S are in same direction. Like pushing an object. Okay? It is a positive object. Yes, 3. Negative object. When is the work done on the body negative? Yes. So then theta is 180 degree between force and displacement, right? Cos 180 is -1. Therefore W is Fs cos 180 equal to -Fs. Just equate. What is the example of this?
Magnetic repulsion.
Huh? Magnetic repulsion. So if it is repelling, Both are going away. So how it is negative? When this man is going in this direction, right? Where is the friction acting? Frictional force is opposite direction. So in this situation, right, displacement is on the right, the frictional force is on the left. So the angle between displacement and force is 180 degrees, right? So in the same situation, gravity is not doing any work, but frictional force is. So like I said in the beginning, it is the force which does the work, right? In this situation, when a man is carrying a load on his head and moving, right? So work done by frictional force is always in the opposite direction to displacement. Because friction always acts against the motion. It is always negative. Clear? So all the scenarios are clear, I think. So this is all I wanted to talk to you about work done. Next topic is power. So I will let you write it. Let me first complete this also. What is power? Power is defined as rate of doing work. That is E is equal to W upon T. Okay, rate at which work is done. So therefore, and what is the unit of it? It is watt, joule per second. So this is joule per second of watt. Okay, so work done unit is joule and time is second. So joule per second of watt. Now, if we expand work further, work is force into displacement upon time. And displacement upon time is velocity. So we have another formula for power. So these are the two formulas for power. This is mechanical power, and this can be used in electricity. When we say watt, right? So we will see that. Right? So this is Newton meter per second. In this case, which is again can be expressed as. So any object on which force acts and it causes a velocity v in it, the product of force and velocity is the power. It's the amount of work being done on the object by the force per unit time, right? That's what it is. Okay, you can write to here. So if you want to underline in your textbook, that is also okay. Locate description, just to save time. Writing is good, but those who are not writing, you can underline your textbook. Done? Finished? Can I proceed? Okay. So, what is energy? So, it is ability or capacity to do work. Physical work, right? So, we cannot work if we don't have energy, right? So, therefore, energy and work, they are interchangeable. If we work on a body, we increase its energy, right? So, what is the unit of energy then? Joule, right? It's both are interchangeable. Work and energy are interchangeable, right? So, unit of energy is also joule, right? Since both are differently addressed, but essentially both are same, right? So, energy and work complement each other, right? Interchangeable. Because if you don't have energy, you cannot work. When you are doing work, your energy is reducing. correct? And when you work on a body, the energy increases. So can you give me example? How can, like, let us say if we have, so first let us understand how many different types of energies are there. Then it will become more clear, right? Energy types. How many types of energy you can think of? One is mechanical. Most obvious is mechanical energy. Of course, we are going to study in the next chapter in more detail. So, what is mechanical energy? What is mechanic?
Kinetic energy.
Mechanic is to do with motion, okay, or the state of a body, right? So, we'll explore this in more detail. What are the other types of energy you are familiar with? Which is the most true essential energy needed for our survival? Solar, even light. Okay, and for our survival, most basic energy I must. Sound like, I mean, in silence you can't survive. I would love to be silent. Like, is it essential? Light is essential.
Heat energy.
Heat, yes. Why? Food, right? So these are the most basic form of energy required for our survival. And all the energy that I'm going to list down, they can be converted into this. So the good thing about energy is it can be converted from one form to another. Like we have this light energy. From where is it coming? Electrical, right? We have electrical energy. From where it is coming? Mechanical, right? So we'll see that. Okay. So all that energy that I'm going to list down can be converted from one to other. And physics is all about studying that. Physics is that branch of science which deals with study of energy and its conversion from one form to other. That is physics. We study energy in physics. And in all other branches we use it. And the whole world, all the wars happen because of this. Everybody wants to have a bigger pie of energy resource. Whether it is Gulf War or the current war going on in Ukraine and Russia, or all the war that US launches, right? So in that, it's always energy security. Okay. It's a very touchy topic. So what are the other forms of energy? Electrical. Electrical, right? Chemical. The heat, light. Right. Somebody said nuclear. Yes, it is. Nuclear. Yes. 6, 7. So that's it. Sound. So these are the 7 most basic different forms of energy. All others are, they can be mapped onto this, right?
Magnetic energy.
It's part of electrical. So it's always electromagnetic. Okay. Any other energy you can think of? Huh? Solar is light. Wind is mechanical. Movement, right? Motion. So these are the broad energy categories. You should not forget this. Rest everything can be mapped onto this. Okay. So good thing is they can be converted from one form to another. Now let us get familiar with energy units. So what are the energy units? Energy units. So I think in this topic there are 3 separate chapters. First I will finish the entire theory of 3 chapters. Then we'll take numerical later on for all 3. Okay. So yeah. So what is the unit of energy? It is joule. Right? So in different energy domains, we have different energy units, right? So joule is the SI unit of energy. Okay. So in electrical domain, we use what is called as kilowatt hour. Watt is power, not energy. So energy is work is energy, right? So energy is power into time. So kilowatt is power, hour is time. Okay. So the electricity bill that comes in our house, okay, it is in terms of units, electrical unit. So one electrical unit is equal to 1 kilowatt hour. And all this unit can be converted into joule. So what is 1 kilowatt hour equal to? Kilo is watt is watt, SI unit already, and hours is 3600. So this is joule. 3.6 into 10 raised to 6 joule, 1 kilowatt. Got it? So every unit can be converted to that. So for heat, we have another special unit. It is called calorie. Okay? And 1 calorie is given as 4.18 joule. Okay? So like when we eat food, so that energy is in terms of calorie and kilocalorie. So how much is 1 calorie? That's, but how do we define it? So whatever energy is required, okay, to raise the temperature of 1 gram of water, which is at 14.5 degrees Celsius by 1 degree. So we increase it to 15.5 degrees Celsius. Whatever energy it takes, that is called 1 calorie. Okay. So that's 1 calorie. In atomic and nuclear field, we use an energy unit called electron volt. What do we use? Electron volt. And how much is 1 electron volt? So 1 electron means, what does it mean? It is the amount of energy gained by an electron when it is accelerated by the potential difference of 1 volt. Are you familiar with potential difference?
Yes.
Right? So obviously, when I have a potential difference between these 2 points, let us say A and B, right? 1 volt. And if I drop an electron here, then this electron will race towards the other terminal. So whatever energy, so it is racing, so it will have kinetic energy. So whatever energy the electron gains when it is accelerated through a potential difference of 1 volt is 1 electron volt. So how do we write it? What is the charge on the electron? 1.6 into 19 coulomb and into 1 volt. So this is joule. Coulomb is SI unit for charge, volt is SI unit for potential difference. So SI, this will be joule. So I gave you different energy unit and also told you how much joule it is. So joule is the standard SI unit for energy, and all the other units of energy can be converted back into SI. Okay. So just write this down. So this is all in this chapter. Next we'll start with next topic, which is mechanical energy. Yeah. I think this is chapter 2B. 2A finishes here. So 2A, 2B is from Selena. Selena name of the topic, right? In your volume, I think it is continuous. So So if you look at all these topics, right, except for chemical, in your 10th course, we are going to study about all this, right? So if you look at your chapter name, it is named after, these are the name of the chapter, right? Optics, light will be covered there. Modern physics has been applied. Sound, you have a chapter. Electrical, you have a chapter. So in this chapter, we'll be studying only about mechanical energy. Okay. So physics is all about learning about energies. Is everybody done writing? So let me explain different types of mechanical energy and then we'll close. So there are two types of mechanical energies: potential energy and kinetic energy. So what is the difference between the two? Can anybody tell me what is potential energy?
The energy comes,
Yeah, go ahead.
the energy possessed by a body is the rest.
Okay, so what does it mean?
If the body is going to move, then the energy is possessed by the body.
So right now this
Just
duster,
stored energy.
yeah, so does it have any energy? Huh? It has energy.
Yes.
How will you show me that it has energy?
So if you drop it.
Yeah, so drop it then you will see, right? So let's do it again. I always like it. So this duster is there. Does it have a energy right now? Let us say this is up. It cannot go below this. It has energy right now. It has energy right now. I cannot drop it. Let's say this is up, ground. It has energy. How will you show?
So if it moves, then it will have kinetic energy.
Kinetic, but it is in rest position. We are discussing potential, so kinetic will be here because it is not moving. But if this is your Earth surface, does it have energy right now? No. Okay. So at ground you don't have any potential energy, right? Now what I am doing, I am lifting it up. So from ground, I took it to this height edge. So what did I do?
The distance.
So it has completed this displacement and I applied force on it. So I worked on it. Okay, listen. I worked on this object. So when I work on this object, what did I say? Whenever you work on an object, its energy increases. So now it has got some energy because I lifted it. What happened? When I removed it, what happened? Sound. Is it energy? Okay, it is energy, right? So that was the potential energy which was stored. It got converted into sound, right? So when I am speaking, all my calories are burning. Okay, 2, 3. I have a capacity. I cannot endlessly speak. I can only speak till I have energy, stored energy. Okay, so the stored energy is potential energy. And it becomes visible only when it is converted from potential to kinetic. Okay, so kinetic is energy in action. So you store energy to do your work. All the work is done through kinetic. Okay, so when you have battery in your mobile, when you charge, you are working on the battery. So the energy is stored. And then you unplug it. So now it is working till the charge lasts. So when you charge, you are storing the electrical potential energy. When you use it, energy is usage of energy is generally kinetic. You will understand in case of mechanical, right? So what is potential energy? Energy. So how did it get energy? By virtue of its state of rest or its position. So energy is stored in a body by virtue of its position. Okay? Or change in configuration. So there are two types of potential energy. Right? Where is that pen? It is the energy associated with the body by virtue of its position. So of rest, right? So by virtue of its position or change in its configuration. Right? So position example to be solved. What is change in its configuration? We call it elastic potential energy. So I have an unstretched rubber band. Right? So I am holding it in front of me. And then I stretch it like this. And leave it. What happens? It will hurt you. So when I change the configuration, so its natural state of rubber was relaxed. Right? But when I altered its state or configuration, then it got some energy. So that kind of energy is called elastic potential. Okay? So you must have realized how the potential energy enters in the object is whenever we are working on a body against some force acting on it. So there is a gravitational force acting. So whenever you work in a situation against some force acting on a body, only then there is potential energy involved. Right? So in rubber, what happens? It is an elastic body. So it will try to regain its original. So I am working against the restoring force. Right? Or a spring. A natural relaxed spring is its original state. So either I stretch. So when I stretch, there is a restoring force in opposite direction. When I compress, again the restoring force in opposite direction. So whenever you are working on an object against some force, then potential energy enters in there. Okay. Now what is kinetic energy? Which marker will we use? So kinetic energy is the energy associated with the body by virtue of its motion. Right? So this is easy, right? Right? So whenever sound comes, it's energy, right? Earlier, right, no energy, no sound, right? So this is kinetic energy, okay, so you're not going to throw duster on each other, right? Because here, sound won't be heard, but Okay.
The sound will produce noise.
Oh,
So when we get hurt, that will produce noise.
oh, if it lands like this, no sound. Cushioning effect. Okay, fine. So more on this later. Okay, so see you in the next one. I mean, if you want more, we'll see again in the next class. Hope the concept is clear. Okay.
Let's say